All right. So we left off. I kind of introduced this idea of doing the difference in two populations, specifically thinking about means here. Let me make sure I'm recording this. Okay. I'm not going to blow this up, but I'm just going to run up here. So I think the issue when I use this is that when it switches to the presentation view, I think that's what's screwing with the HDMI. So it's a little bit small. If you can't see anything, make sure you kind of ask. We're a little bit smaller here. So let's say we're looking at the difference in two sample means, and we worked through examples where we had known population variances. Instead, we're going to work through examples where we have only sample variances. Okay. So we jumped ahead a little bit. We just kind of skipped the proportion stuff. We'll kind of keep working. So everything's going to be exactly the same. I said, don't worry about this step. Finding our degrees of freedom, it was that real nasty equation. I'm always going to give you the degrees of freedom, okay, for these two population examples. So all the steps are exactly what we did with one population where we had a sample mean and only had a sample variance. It's just now we've got like twice as many parts. And it's a little bit harder, right? There's a few more things moving, but all the principles, the same steps all apply, right? So here I've got only sample variances, so I have to calculate my degrees of freedom with this nasty equation. And then I'm centering my confidence interval around the sample difference I find, or the difference in the sample means that I find, okay? I then go a certain number of standard deviations out, but now I get that from my student t-distribution because I only have sample variances. Remember, I'm dividing by n-1, so it's going to kind of skew my standard deviation a bit. So we said they won't be standard normally distributed. They're going to come from a student t-distribution. I then multiply that by the standard deviation of the difference in my sample means, which was basically just the square root of, we took each sample means variance and add them together, right? Because the variance for each sample mean would be the sample variance of the data you sampled from over the sample size for that group. Okay. So this looks like just like what we did last class. It's just we've replaced the population variances with sample variances, and we have to use the student t-distribution. Okay. So we'll walk through this example. So I've got, let me make this big. I can kind of write things down, and I'll switch to this eventually. I just want to have it so I can't see the slides now when I go to write here. So I've got I've got texters, non-texters. So the sample mean for non-texters was not $1. My mind is gone from this week. 1.3 seconds. The variance for non-texters response time, 0.16 seconds. And I had 49 of them. The texters were what? Sample sizes 64. Their variance 1.44. And then their response time 2.36. Okay. So we want to build a 90% confidence interval for the difference in the response time for these two groups, right? Texters, I think I had non-texters minus texters. Right? So that sample difference is going to be take the sample mean for non-texters, subtract the sample mean from texters, right? So we've got what? 1.3 minus 2.36. That's what my confidence interval should be centered around. Okay. So when I'm looking at this right away, I know that my confidence interval should be centered around what? About -1 or -1.06, it looks like. From here, it's just a matter of plugging everything else in. So I've got to look up this t-value eventually. But here, this standard deviation for the difference in my sample means is just the square root of each group's sample variance divided by that group's sample size. Right? So now it's just a matter of plugging my values in here. I could write this out, but it's, I think I'm trusting you guys. Like you can plug in the sample variances and the sample sizes here. The only thing left to do is really look up this t-value I need, or the number of standard deviations where I need to go. The 90% confidence interval alpha would be what? 0.1. So I need to look up alpha over 2 or 0.05. Now I'd have to give you one more thing here, which is the degrees of freedom, right? So I'll kind of ignore my meme for a second because I'm afraid to switch this to presenter view. I used that nasty equation, came up with my degrees of freedom. I said if I ever had a decimal, I always rounded it down to err on the side of caution. So degrees of freedom of 80. So I go to that T table, degrees of freedom 80. The area I wanted in the tail was 0.05. Or I shouldn't say tail, in the tails was 0.05. So 1.664. Right? That's that T value that I needed. That'd be the last thing I have to plug in. Right? And now it's just a matter of getting these entered into a calculator. Like I said ahead of time, I would maybe calculate this first. Right? Then I only have one value to plug in here. Kind of cutting down on kind of how much I have to enter in one line on my calculator and how many parentheses I need to use. Okay. So not a whole lot different than what we were doing before, other than when we looked up that student T value, we had to kind of use some given degrees of freedom. I had to give that to you. So, any questions over anything there? Yeah.
Are you giving us a T table? Or
I'll give you, so your exam will have a student T table, a standard normal, and that formula sheet that's on Canvas all within it. Yep. So if I put all those values in, I get negative 1.3 to negative 0.79, right? So how can I use this confidence interval? Well, confidence intervals are most interesting when they only include positive or they only include negative values. Because if they don't, right? So this was what? Negative 1.3, excuse me, to negative 1.3 to about negative point, I think it was 0.79. So here, with 90% certainty, I can tell you that the difference in response times is somewhere in this range, right? So if they're all negative values with 90% confidence, I can tell you that what? Non-texters have quicker response times, right? Because if this is negative, that means that their response time is quicker, which is a good thing, right? The longer it takes you to respond when you're driving, that's a really bad scenario, okay? So because we found that that difference is negative, we know that that must mean texters are taking longer to respond with 90% certainty. Okay. Questions on that? So why I say it's not interesting if it like ever crosses over zero. So think about if I had this, right? What if it was like negative 1. Thank you. What if it was negative 1.3 to 2.4 or something? Well, now the difference in response times, it could be that texters are taking longer to respond. It could be, though, that this is positive and that texters are actually responding quicker to things around them. Or potentially, there's no difference, right? Because confidence intervals are creating a range of values that we say with 90% confidence, it's one of the values in this range, right? Well, if that one of those values could be zero, there might be no difference. Any questions on that? Okay. So I've got another example here. I think I've got a couple, but I want to, for the sake of time, want to make sure that we go through this one. Okay. I might come back to this one later. It's just another confidence interval example where we've got brands for cigarettes. You've got two sample sizes, two sample variances, two sample means. I think the kind of step that's really difficult that I'll kind of walk through with you, because I mean, once you identify, so if we go to our formula sheet, once you identify your confidence interval equations, I mean, it's really plugging values in. The only thing that's kind of tough is that you have to find that Z or that T value, right? I think that's maybe the slightly harder part. So if I'm looking at this formula sheet, right, here's my three confidence interval equations for two populations. I mean, once I know that I only have sample variances, I'm always going to just say this is my equation and start plugging my values in. I'm giving you the sample means, sample variances, and sample sizes. So really the toughest part about these are looking up those T values. So for this one, if I give you this degrees of freedom of 42, what would your alpha be at the 95% confidence interval? Yeah, 0.05. I didn't have it there. I had it here. The formula sheet reminds you, oh yeah, you got to divide alpha by 2 though. There's half alpha on each side of your confidence interval. So when you go to these t-tables at degrees of freedom of 42, I wanted half of alpha. My alpha was 0.05, so half of alpha is 0.025 at degrees of freedom 42. That t-value I need to use in that confidence interval construction will be 2.018. But once I have that, it's really just a matter of plugging everything into those equations, right? Coming up with my upper and lower bound, adding that margin of error to my upper bound, subtracting the margin of error to my lower bound, okay? Any questions on this? All right, so we'll do a little bit of hypothesis testing here. Also, I cannot for the life of me remember, and it was the day that I didn't record in here. When we went through those Excel examples, did I only go through one type with you guys for one population? So we were looking at, I remember, so I had this and I just couldn't remember if I didn't save it, but I know that we looked at, did we look at like e-cigarette stuff at all? Okay, we did this one though. We looked at like, we did something with a BMI. Okay. I'm going to save a little bit of time. So I didn't realize that I didn't do it. I did it in my non-honors section after the fact. And I thought, I couldn't remember if it was the day that I didn't record. So I'll show you a little bit of how you do that hypothesis testing. It'll just be some good review as well. Give us different examples for one population. But I realized that last part of your Excel assignment, which I had that set right to be due Monday. Yeah, so I'll make sure I do that so that if you're having some difficulty with those last ones, you probably could have figured it out from like what we have done. But I just want to make sure I show you something very similar and then kind of get that saved. All right, so sorry, that just came to me when I was thinking about, we're about to go into hypothesis testing, right? So we're into some hypothesis testing where we don't know the population variances, okay? So our steps are literally exactly the same. Nothing's changed. The only thing that's going to change is how we calculate our test statistic, right? Now, we said before, right, we had our test statistic when we had sample means and known population variances. It's not going to change at all. The only thing that's going to change is that we, instead of using population variances, are using sample variances, right? We still need to use this equation to find our degrees of freedom, but once again, in all these examples, all the problems on the exam, I'm going to give you that degrees of freedom. It's just a practice and computation for that one. That one's wild. So, what did I say we were always going to use as the assumed true difference? We still have 3 different types of tests, can be greater than, less than, or not equal to. But I said I'm always going to keep that assumed true difference as 0, right? So it's almost like you can kind of ignore this part of the test statistic equation for what we're doing, right? Simplifies a little bit. So it's now, our test statistic is what we would call a t statistic because it's coming from a student t distribution, right? So I've got some of the answers here, but we'll like work through and identify why they are what they are. So let's say that we want to see whether or not there's the kind of difference in salaries between male and female doctors, right? So we can use this hypothesis testing between 2 populations to do a lot of like gender, race discrimination stuff. See if there's differences across groups in their pay or whatever it is, right? So I've got 41 male physicians, 41 female physicians. I have their sample means, I have their sample variances, right? And I want to test for whether or not there are differences in their salary. So once again, kind of similar to one population, if I want to test for something as different than, right, or there's differences in these 2 groups, I'm really just saying, is that true population mean for males not equal to that true population mean for females? Which, if I'm thinking about the statistic I'm looking at is really the difference, right? I need to kind of rearrange this a little bit, right? Subtract the mean for females from both sides. And what I'm really saying there is the difference between those 2 anything other than 0, right? If I'm saying, are the average salaries for male and females different from another? Are they not equal to each other? I can rearrange that to say, is that difference something other than 0 between the 2 groups, right? This is supposed to be a D, not a 0. It looks even more like a 0. There we go. Okay. So go back here. We've got a two-tailed test, right? The next kind of step is, what are our critical values? So I asked you to find one critical value here. We could find several very quickly. So what would the critical values be for the 1, 5, and 10% level? Well, if I've got a two-tailed test, right away, I should have been able to rule out C. Because we said for a two-tailed test, which is, we have a not equal to sign here, we're going to be looking for the T values that give us alpha total in the tails. Right, so this one, I think we were looking up an alpha of 0.01, or no, I think it was 1% significant. Yeah, so 0.01. So there's alpha of 0.01 total in the tails, which means that there's half of alpha in each tail. So it kind of goes back to confidence intervals for a two-tailed test. I said this to someone, to my other section, if this helps. Anytime that we have, we're going test statistic and trying to find our p-value. If we're doing this on the standard normal distribution, this was kind of like use the row and column headings, and then you're finding a value in the middle. Whereas when we have alpha and want to find critical values, you're kind of looking up that probability in the middle and finding kind of the corresponding row, column, heading, right, which tells you that kind of Z value. So I don't know if that helps anyone, but that's what we're doing here, right? We know that probability, or we know the area in the tail. We want to work in reverse to find what are these two T values that would give me those desired alpha over 2's in the tail. So my degrees of freedom is 80, right? So I'll go to my T table. I wanted 0.01 divided by 2, so 0.005. Add degrees of freedom of 80. Looks like that's 2.639, right? So I have positive and negative of the same value. I've got a pair, like each alpha would have a pair of critical values here. And I can think about my rejection region, drawing arrows kind of into the tails there. So the next step is going to be, I've got to find my test statistic here. Okay. Excuse me. Now, if I look at the sample difference that I found, so I've got 174 and 141,000. Okay. So what I'm thinking about is, I know the distribution for the difference in these sample means should be kind of centered around that assumed true difference, which I'm always using 0 here. So I had what, 171. Let me make sure I get these numbers right. 174 and 141. Okay. So 174,000 minus 141,000. That was my male and kind of female averages. I'm not doing confidence intervals, real hypothesis testing. So I've got this sample difference of what, 33,000. So the sample difference I found is somewhere over here, right? Okay. Now, if I have a two-tailed test, and I'm thinking about my p-value, I could find that area to the right, but I would then have to do what to get my total p-value? If it's a two-tailed test, equally as likely I saw something on the other side of the distribution that went against the null. So once I find the one area, I'll multiply it by 2. Okay. Now, I already mentioned using a student t-table. That's a lot more difficult to do because sometimes we can only put it into ranges. So I won't ask you to do that. If I ever ask you for a p-value from a student t-distribution, it would be exactly one of those values you could find. So from here, right, this was actually like the numerator of our test statistic, right? Because we were subtracting the assumed true test statistic, assumed true, not test statistic, assumed true difference of 0. We then divide by the standard deviation of our sample means, which was just each group's variance over its sample size. So I'll go back and use the slides to kind of depict this to you. So all I'm doing there is, right, plugging in those variances and those sample sizes. I had that sample difference there kind of in my numerator. I end up with a ridiculously large test statistic here, right? So despite the variances being pretty high, right, if the assumed true difference was in fact 0, I am 23 almost standard deviations away from that. So my p-value is going to be approximately what? Yeah, hopefully we're getting used to like being two standard deviations is pretty far away from the mean or the assumed true mean or the assumed true difference. 23 standard deviations is like what I assume to be true must clearly not be true, right? So if I'm thinking about what I just found there, this is so like this p-value, this area is essentially 0. So what's probably true is my assumed true value is not true. It's much more likely that the distribution of sample differences here is centered around a much higher value, right? I found really strong evidence that there's a difference between male and female physician salaries, so much so I can reject the fact that there is no difference, right? In fact, I'm guessing if we wanted to start running through this, we could probably reject like even 10,000. We could reject 20,000 as being the difference, right? We have very strong evidence that kind of males kind of have a higher starting, or at least higher salary, physician salary than female physicians, right? So we can do this like in whatever sector we wanted to identify if there's like wage discrepancies or disparities across different groups. So pretty useful. Like these t-tests are pretty useful. And like I said, I don't call them t-tests, but I know that you'll start hearing called that in some of your other courses as you kind of work your way up, looking for differences across two groups. Okay. Any questions on that? All right. I had some old stuff in here. I think what I'm going to do, I kind of have the exam written, but I think I'm going to be nice. Also, I just don't care as much about these about the two population stuff as some of the stuff I want to cover after the exam. I'll just expect you to know how to do sample mean examples when it comes to two populations. So if you have that formula sheet, I'll still give you the same one. But when it comes to the two population confidence intervals and two population hypothesis testing, you shouldn't have to use those equations at all. So if I'm looking at this, right, that's the wrong one. It's from my other section. We're not going to go over this. We're not going to kind of cover this difference in proportions. It's not that much harder, but I don't want to waste time today. I rather would show you that stuff in Excel, and I'd rather do some review on Monday for the exam. Okay. Also, you don't have to worry about this. Okay. So we're just going to be doing differences in population means, kind of using our sample means as evidence when we have known population variances and known sample variances. It's really not a lot different with proportions, so we're not like missing out on a whole lot. And we've already done it with one population, so we can kind of imagine probably how it would go. But yeah, you won't ever be using the two population confidence interval or test statistic equations for the exam. Okay, which probably means, yeah, we should be okay. All right, that should be the only thing. What would be easier for you guys? I can update the formula sheet and give you one without those on the exam. Or if you've already been using this one, I don't want to like screw anyone up. I don't know how it would, but Do you guys have a preference either way? All right, I'll probably go in. I'll probably, if I can do it very easily, get rid of them so that it looks nice still. I'll just probably get rid of them and repost that formula sheet. But that might not happen until later this weekend, maybe like on Sunday. All right, so could happen this afternoon. I just don't know if it will. I have a feeling we get bogged down with stuff this afternoon. So, all right, so let's do. So we don't have to worry about that proportion stuff. Right? So basically, that's everything that we're going to have on the exam. Okay. We'll do matched pairs after the exam, which is kind of interesting and somewhat related to this. But then we're really going to do a hard transition into something called ANOVA testing and linear regression, right? It is my favorite stuff. I think that you guys will enjoy it more. It is not near as computational. It's a lot more thought-provoking. So let's do a little bit of Excel work, though, with this hypothesis testing. And we will start with, I think you could probably, even from what we did in class, probably figure out, I believe it's problem 3 on the Excel homework, where you're looking at drivers' ages or whatever. So that would be very similar to the one that we worked in class. It's just that instead of the normal distribution, we're using the student T distribution. So I've got kind of the average age that someone tried e-cigarette, right? So this is like high school and middle school kids. That also sounds like such a, like, I don't know, boomer term or something, but like the electronic cigarettes, right? Juuls, like, well, all these different things. I forget the exact question they asked the kids, but so from that age they first tried electronic cigarette, I calculated the sample mean, the sample variance, right, and the sample size. I got a really large sample here, right? So maybe I want to do something to start out with. I just want to say, okay, is the average age that someone tries one of these electronic cigarettes different than 15? So not equal to 15, right? Well, I can use Excel here to essentially just be my calculator, okay? So we're back to these one population examples. I'm just going to take my sample mean, right, the statistic I'm interested in, subtract the assumed true value of that statistic, right, and then divide by the standard deviation of that statistic, or the standard deviation of your sample mean. So that would be the square root of your sample variance divided by your sample size, right? I'm literally just using Excel to be my calculator. There's no built-in formula or function there. It kind of sucks, but it is what it is, okay? So we got that. We then, I'll skip the p-value for a second. We can also look up our critical values, right? Well, remember, if I know the area in the tail, and I want to find the corresponding t or z value, I'm working in reverse, or the inverse, right? So here we would do, instead of norm.s.inv, t.inv. It's a two-tailed test. So what area do we want in that lower left tail or the upper right tail? 0.01 divided by 2. Right? My degrees of freedom would be the sample size minus 1, right? And this should give me the negative critical value for this two-tailed test. Well, I also need to somehow indicate that there are, in fact, 2 critical values at that alpha for a two-tailed test, right? One on either side. All right, so all I'm going to do there is take the absolute value of that negative critical value I found, because I know it's the same value but positive on the other side. Anyone want to see any of that again? Did you go a little bit too quick? This one?
Yeah, I just missed what you did on after that.
So this is my degrees of freedom. So all I'm doing there is sample size minus 1. I guess technically I could have typed the number, but I always use cell references to, to show you the value of them. So I've got my critical values. I could also come up with my p-value. So this is where doing this by hand was hard with that student t-table. So instead, I can find like any test. I can look up any test statistic if I use Excel, because it basically is like, it does the integration. It doesn't really have a table stored in it, right? So I'm going to tell it t.dist, right? So just like with the standard normal, instead of norm.s.dist to look up a z-value and find the area to the left, which is what our p-value would represent, I'm going to use the t.dist function. Okay? So here's my test statistic, comma, Degrees of freedom is my sample size minus 1, and then comma 1 makes it cumulative. Okay, so this is going to give me the area to the left of that negative test statistic. But it's a two-tailed test, so what else do I need to do? Yeah, so the way I multiply by 2 is on the outside of this function, right? Whatever that function returns, I'm just going to multiply that by 2. Okay? Any questions on that? Okay. So we'll hit enter there. Now, I'm 32 standard deviations away. So my p-value here is very, very close to 0. It's wild to me that even Excel stores things out to the 200th decimal, right? This is wild how great computers are. So, I mean, I guess it's not that interesting, but so we've got a p-value is basically 0, right? There's another way I can find this as well. Okay, so if I can remember correctly, there it goes. Excel is kind of nice. It starts to, for some of this hypothesis testing stuff, have a lot of built-in functions. Okay, so this one t.dis.2t, all you have to do is tell it your test statistic and your degrees of freedom. And it'll basically like multiply it by 2 for you. It's kind of funny to me that someone literally took the time to write a function that the only additional thing it does is multiply the end result by 2, but it's in here, right? However, it's very annoying because it looks like it doesn't work here, right? For whatever reason, the way they have this program, so this, I'll rant a little bit. So they go through all this trouble to write this program that the only additional thing it does is multiply it by 2 for you. But they don't write in that for some reason they coded it to be looking at the right-hand side. So if you have a negative test statistic for a two-tailed test, you need to take the absolute value of it. Now, it'll give you exactly what you found before. I have no idea what genius came up with. That was the way that they wanted to code it. But for whatever reason, if you want to use that t.dis.2t, you have to take the absolute value of the test. That's just the way that it's not programmed to work with negative values. I would suggest like just you get used to using that t.dist and multiplying it by 2, only because like I like to think about it that way because that's how you would do it by hand, right? And so those kind of two things line up a little bit better. Okay. Yeah.
What's the difference between the 2T version and the RT version?
So I don't usually show you this because I don't think I have an example on here. It's right tail, but it's basically just right tail. So, right, if I had a right tail test and I had a negative test statistic, which would be a case where I found something that supported the null. So why am I going through the process anyways? But if I did, this should give me basically 1. So, oh, I forgot to put my degrees of freedom, didn't I? Right, it's giving me the area to the right for a right-tailed test. So, so yeah, you can use. So, I don't believe. Yeah, so it's actually interesting. So I didn't show you that, I don't think, before when I showed. Did I show you something with this? No, I probably haven't. I haven't probably showed you the functions in Excel for the student t distribution. So that one's nice, where I can find the area to the right of a certain value. Notice like for the norm, this was the one that's frustrating because it only ever has the area to the left. I don't know why they don't just write in some so that like you don't have to do the 1 minus yourself and it just looks for the area to the right. Like they clearly can program it for a much more difficult distribution, which is this wild, like hundreds and thousands of student t distribution formula. So it's like I don't know. But yeah, it kind of does that nice thing where it looks to the right. Any other questions there? I probably shouldn't be putting this on YouTube. Like Microsoft is going to think like I absolutely hate their workers or whatever. But I just think I would do things differently. So coming up with the rejection decision, this is where I said you can kind of get fancy. You can just compare the p-value to alpha here. Clearly, the p-value is way less than alpha, so we should reject. You can get fancy and do the if statement where you say if this p-value is less than alpha, comma, put in the word reject, comma, if it's not, no, then we fail to reject. Okay. So if I hit enter here, clearly reject. Yeah.
Do you like always put if like the p-value is less than alpha, or is it ever thinking that it's
So you're always checking to see if the p-value is less than alpha, because you want to determine if you can reject. If that p-value is less than alpha, then you can reject. Okay? So yeah, you're always seeing if p-value is less than alpha. If it's not, then you fail to reject. Any other questions on that? Okay, so this is kind of interesting, like to make a point here. So I was testing to see if the true age or the average age when someone first smoked electronic cigarette is 15. I found 14.2 as my sample mean. That doesn't seem wildly that far off, but I can still reject 15 with an insanely high level of confidence, right? That p-value is about 0. But it's because I have such a high sample size. If I start getting sample sizes in the thousands, that distribution of my sample means is like so high or so peaked that if I see anything that's like even remotely a little bit away from that assumed true value, I know that that was very unlikely for me to see. That my sample mean will be very informative about where the true population mean is. And that's kind of intuitively makes sense. We got 6,000 people. That sample mean is way more likely to be close to the population mean than if I have a sample mean from 5 people. That could be way off, right? So kind of interesting. You know, we could boil this down. I think I can reject 14 and a half. I can reject, I think all the way down to like 14.3. I'm still rejecting it. 14 and a quarter of a year. Okay, now maybe I failed to reject at the 99% level, right? So having this high sample size, we can really narrow down where that population mean value is. Okay. Any questions on this? I'll show you a proportion example in Excel as well, because I think that's problem 4, right? The proportion of people that get tickets or something like that. So this one I also found kind of interesting. So I'm going to start out with a hypothesis test that more than 25% of kids have tried an electronic cigarette, right? So I have this high school, middle school kids. So I've got ever tried cigarette, 0 if they haven't, 1 if they did. I can find the sample proportion by taking the average of this 1, 0 variable, right? Or the mean of this 1, 0 variable. I then found my sample size. Here I had a much smaller sample, so maybe things will be a little more interesting. So once again, I'm just going to use Excel to be my calculator to find the test statistics. So I'm going to take that sample proportion, subtract the assumed true proportion. And then before, in the other example, I divided by the standard deviation of my sample means. Well, now I'm dividing by the standard deviation of my sample proportions. So the square root of the assumed true proportion times 1 minus that assumed true proportion divided by my sample size. I'm just taking that test statistic equation and entering it into Excel so I don't have to type the numbers and I can just click on the numbers. Okay. So once I come up with this test statistic, right, I'm going to have a Z value. I know how many standard deviations away from that assumed true proportion my sample was. So if I was using t.dist before, proportions are always examples where we use the standard normal. So instead of t.dist, I'm going to use norm.s.dist, right? Look up that Z value and then comma 1, right? This is where your question about the RT would be really nice to have the norm.s.dist.rt, right? Because I need the area to the right for a right-tailed test. All this is going to do is tell me the area to the left of that test statistic, okay? Which is fine, right? But I know I want the area to the right, so I'm going to go in and then just have to subtract that from 1, right? That way, if I know the area to the left, 1 minus that would give me the area to the right, okay? Any questions there? Do you want to see maybe this again? I don't know. Makes me look like you're working along. Questions there? Okay. So from there, we can also find critical values. This is where we know the area in the tail. We want to find the corresponding Z values now, right? So that was t.inv. So now it's going to be norm.s.inv. Here I had an alpha of 0.01. It's only a one-tailed test, but it's a right-tailed test. So I can just simply have it look up that value of alpha. But for a right-tailed test, my critical value is on the right side. That should be positive. Well, it's symmetric. So I could just look up alpha and take the absolute value. Or I could think about, well, alpha is the total area in my right tail. So the area in the left tail, which is what I need to tell this function, norm.s.inv, would be 1 minus that, right? So I could have taken the absolute value because I knew it was a symmetric distribution, or I could actually look up the actual area to the left, which would be 1 minus alpha here, okay? And then same kind of thing as before, my rejection decision, if that p-value is less than alpha, comma, put the word reject in there. If it's not, put the word fail to reject, okay? Any questions on that? So now I've got my rejection decision, right? I just barely failed to reject here, right? 0.02 is just slightly above 0.01. But I thought this is kind of an interesting example as well. You look at this and you've got quite a bit smaller sample size, but even at 100, right? I found a sample proportion that's pretty far away from this assumed true value, and I can't quite reject it, right? So this shows the importance of having a higher sample size. Yeah.
So in Excel, you can do the same thing, except you can compare the test statistic with the critical value, right? In that case,
Right here? You mean to do the rejection decision?
Yeah.
Yeah, yep. You could also do, if this test statistic is greater than my critical value, put the word reject. If not, put the word fail to reject. Now, hopefully, if I start changing this around, right, they always kind of line up, right? Because I should be making the same decision. Okay. So with 99% confidence or certainty, I couldn't quite reject the assumed true value of that a quarter of kids have smoked electronic cigarettes, right? I can't say it's actually that high. I can't say that it's greater than that, even though I found strong sample evidence, right? But it's because my sample size is lower, right? But what is interesting, if I kind of figure out which values I could reject, I can actually reject at the 99% level that the proportion of kids is kind of less than or equal to 0.2. So what I can really say there is I found strong evidence that more than 1 out of 5 kids have tried an electronic cigarette in middle high school, right? Which I don't know. I mean, I don't think it's like, I don't know if that's high or not. It depends on probably what your opinions are. I think it's probably about what it probably was with cigarettes. Yeah.
Can you like kind of go over like when to use like the norm.si?
Yep. Yeah. So I'll show you one more thing and then I'll get to that because I thought this was very interesting about the data that you guys might find interesting. If I sort this data on the age that someone first tried cigarettes, there's a lot of, or e-cigarette, there's a lot of 9s in here, which I found very alarming. So I just thought this is actual data. Like I didn't make this up. This comes from an actual survey. So I was like, oh, that's alarming. But to your question, I think this is the easiest way to organize everything. And really, we don't have a ton of examples. So if I've got a sample mean and I know the population variance, or I'm looking at the difference in sample means, right? And I've got population variances for both groups, or I'm looking at proportion examples. These are all situations where I use that standard normal distribution. Okay. Whenever I have a sample mean and I only have a sample variance or sample standard deviation, I don't know the population variance, or I'm looking at the difference in sample means and I only have the sample variances for those groups, that's a scenario where we're going to use that student T. Okay. Is that what you were talking about? Yeah. Yep.
And then like there's also like the norm.si.
So when we go back to that, there is a way, and I haven't shown it to you because it's somewhat confusing. But really what norm.dist was, remember, it converted a value into a z-score for you. So remember it like calculated the z-score and then looked it up, but did it behind the scenes. So you can actually use, when we're doing this, if I did like norm.dist and I told it the sample mean that I found, I then told it, the problem is, the reason why we can't use norm.dist anymore is because I need to tell it the true population mean. But you can imagine for hypothesis testing, I could tell it my assumed true mean. I could then tell it, I need to tell it the standard deviation here. So I would need the standard deviation of my sample mean. So if here I put the square root of some known population variance over my sample size, it would actually calculate my test statistic for me and then look that test statistic up. So I could actually find my p-values using this. It's just that usually we like to see the test statistic. We'd like to see the intermediate step. And also it becomes kind of difficult because here it says standard deviation in the Excel function, but it's, you know, the standard deviation of your sample mean. So you would have had to either put this in or calculate it in the cell ahead of time. But yeah, pretty much we're going to really primarily rely on that norm.s.dist function. Yep. Any other questions? So I have another video that I haven't posted to our section. I'll try to get that done this afternoon of working through some more of those practice problems for practice exam A. Once again, I think the problems aren't going to quite line up. So I'll in the description kind of put exactly what questions they line up to for you guys. Okay. Other than that, any questions for me? All right, I'll kind of leave you with, oh, I don't want to move this out of order. I got 99 problems, but rejecting the null ain't one. So I thought this was another great meme that everyone should see. So have a good weekend, stay safe. If you have any questions as you're studying, feel free to reach out, kind of set up some time to meet early next week. So we're all prepared to do as well as we possibly can on the exam Wednesday. Okay.